Hello there, this is Al, and I guess this I'll add to the reference section. I wanted to, because I'm using this class quite a lot in the current section that we're at, thought I'd add this to the reference section on this class called TsAddress. I think I mentioned briefly in tutorial what is it now? 185 probably. I mentioned briefly the use of this class for doing simplifying stack walking. I thought I was just going to give you first a quick demo of the most basic usage of this address class, and that is assigning these things. Can be assigned an address of something. Here I have a variable, two variables in the stack, and I'm assigning the address of the variable I into this address object, and k into this address object. The funny thing is, the result of running this program, which I'll let you think for a minute and try to guess what you think the output should be. Keep in mind that k should be, its address should be lower than I. As you declare things, the stack goes down, and so k would end up lower in memory than I. And what do you think that printout should say? Well, if you pause and try to think about it, the answer is that there's no way to tell what this difference is going to be. And it turns out that in this case, it comes out to 12, which is very strange. Now, first I should mention that this difference evaluates to an int. Why? Because there's an operator minus, and this operator is not a member function. That is, well, it's a member, but it's yeah, it's a member. If you take an address and subtract another address from an address, this member uses this member function. And now there's a lot of casting going on here, which is the thing that this class is meant to help you, prevent you from having to do. And the class is a wrapper around a void, pointer to void object. Okay, so any kind of pointer is good enough to construct one. And so this difference is not this is a byte difference between two addresses. So this is just like going back to assembler. The difference between these two is the difference, numeric difference between the two addresses. So that is either a positive or negative integer value. Okay? So you would expect that the answer here should have been 4. Well, it turns out, first let me just do it this way. We'll put these away here. The problem is, the reason why it's getting a weirdo result, I want to do this here, but I don't want to declare those things along together with I and k. So I'll just put these global. Okay, now if I run the program, we'll see that we'll get the answer we expected. Now this just came up when I was trying to think of a way to demonstrate the usage of these of this class. assigning assignment, no casting or anything required, and difference, giving an integer, and I got this weird result. Oh, I still get 12. Now, it's weird. I'm sure that last time I did this, I got 4. Now, this is backwards too. No, k is lower than. Well, let's see. See why that is. For some reason, it allocates 10 bytes, 10 hex bytes on the stack. Now look at that. What the hell is going on here? Now it's subtracting 20 from the stack. And if I remove the show symbol name, it's decided that I is going to be EBP minus 8 and K is going to be EBP minus 14. But they only require 4 bytes. So I did this. This is now a Unicode build. Let me try this with the debug build. The answer seems to be an unpredictable answer because of the funny way that the compiler allocates things on the stack. Oh, I see what I did. I may have declared them in the printf. We'll see. But it still came out to 12, strangely. It's like it's doing an alignment. I should really be EBP minus 4. Now I get 4. You see what I'm saying? It's a very strange thing. This answer is not something that you can guess. It's compiler dependent. However, if you did this, an array of ints, those have to be packed, right? You could do this. Oops. So the difference between, this is not I and K anymore, but K is the same as before, so this should still be positive. This will definitely give 4. 1, the 0th element, no, I don't have backwards. Because it's for an array, the furthest down in memory is the 0th element, because it goes from smaller address to bigger address. The bigger address is the 1th element, so we should get 4. Now, that's not going to depend on the build. Now this just came up at random, sort of a diversion from the topic. But I thought you might find it interesting to know that the way the stack is, that variables on the stack are placed is not given. This will be 4 again. It can only be 4 because this is packed. Alright, now how does this thing work? Well, yeah, I don't even need that global thing anymore. The way this thing works, as you briefly saw, is it's a thing that well, it's constructed by giving it a pointer to anything, right? Which is set here, and all this thing is meant for doing is working with these pointer to void type objects in a simplified way. Now, it is assumed that this is like a linked list type thing. That's just the assumption, because this is mainly for use in dealing with things like stack frames and those sorts of conditions where you're dealing with things that are pointers, but pointers to pointers, so on and so forth. So the operator star here of an address assumes the member, the data, is a pointer to void, pointer, pointer, and then stars that and returns, I guess it would return a pointer to void star. No, return the TsAddress, which can be made from any type of pointer. So really, this should work with just one star here and one. I don't know why I got two. It doesn't matter how you do it. Now that's a little bit weird, right? That it would return that this would return one of the void. That starring an address gives you an address back. But if you think of something like a linked list, right? A linked list node, its first member is usually a pointer to another node, right? So a linked list node has the same property that the star of a node gives you. Star of a pointer, a node pointer gives you a node pointer. This is my linked list class. This linked list class is made up of these. The members are these, or the single member, whatever, is a pointer. As a pointer to one of these things, right? Where's the actual member? It's got two of those, in fact, and also a count. But one of these objects, a node star. Star of a node star gives you a node star, because the first member of a node star is a node star, right? So these sorts of things have that property, and this is meant to have that similar linked list type property. It's a thing that can be dereferenced infinitely many times. I've actually given the description here. TsAddress is considered to be a p-void as well as a pointer to a p-void as well as a p-void. So an expression of the form star address is the same type as an address and allows an infinite number of dereferences. Okay, well that's similar to a linked list. Addition and subtraction of integers is allowed, but only subtraction is defined. So addition of an integer is, addition of integers is allowed. Only subtraction is defined for an address. That is, you can take an address, you can do it. You could subtract one address from another address, okay, and that gives you an integer. But you can't add. Add is disallowed. You can't add one address to another. Because the only thing that makes sense in terms of addresses are differences, okay, which is a signed integer. It's not an address. Right? It changes type. You subtract one address from another, you get like a change of address, and that's an integer value. It's not an address. Now, so an address difference is a quantity. It's not a position in space, and it also implies that addition of addresses is not a meaningful thing. So that's ruled out. It's implemented just as an assertion. I should have this. Well, we should get a linker error and release mode. Yeah, okay. So in debug mode, this is defined. It's not defined with a link. It should have an else here. Just make it a linker and error. By declaring it and not defining it. Right? That's what I put in originally under, a linker error. The reason for defining it at all is to prevent somebody else from thinking that, oh, it'd be a good idea to have plus, and coming along and either modifying this file or making a new object that implements plus. You should run into this assertion or linker error and only get to the point of reading this message first, and so that they understand that that's intended. Plus, no plus for address and address. Okay. Now this operator is fine. Adding an integer to an address is fine, because an integer is an offset, right? But an address is not an offset. Now equals, obvious thing. Less than, obvious. What you would expect. Subtraction is, like I said, a byte subtraction. If I take an address and I subtract 1, it doesn't matter if the type happened to be integer, as you can see. Well, I haven't printed out like -1 here, but suppose I took address of I -1. So I could say address of I is that. And I'm going to show you that those differ by 1 byte. Now, I do have to do this cast though, so just for printf. Now, this subtraction gives me another TsAddress, which I cast that for people. And this print should show that these are differing by 1 byte, not 1 integer. Like not the size of an integer. Whereas if you took the address of I and subtracted 1, that would give you, in fact, address of K, I guess it would. I is here. If I have a bill, the other thing I was just looking at. Change something? Oh, I changed address. Okay, now you can see that the difference here is exactly 1. If I add 1 to this, I get this, right? If you don't believe that, if you print that out in decimal, then that is in fact the case. FF plus 1 is 100. Okay, so that simplifies things. The other thing about these, okay, now there's plus equals, that's fine. So this is addition and an assignment. Okay, now see, you can tell that this is designed for dealing with things like stack walking. Get EBP with value u. Like this is get the nth position in the stack chain, essentially. That's what this does. And it optionally takes as an argument a context pointer. This is the same pointer that is provided by the operating system when a structured exception handler function is invoked. The structured exception handling is set up in such a way that the operating system, it's got nothing to do with any particular compiler, the operating system is designed to, when it's been notified to do so, and an exception occurs, to call a particular function, and one of the structures that is passed to that function is one of these structures of P context, which has this form. Okay, we've got some flags, debug registers, something to do with the floating point unit, segment the variables, the regular registers, ABP, all these things go together. Stack, segment, BP, IP, code segment. I don't know why flags. And I don't know what the must be sanitized means. And then something called extended registers. Now, this is something processor specific, I believe. And the rest is true from 386 onwards. Okay. Now, how does this work? In the case of what this does, well, you can read the thing here, returns to the caller the value that EBP has within the nth function above the caller in the call stack. Okay. And here it's further explained, and I've explained many times that EBP plus 4 star, which gives another address, is the return address of the nth function. So the nth return address is the nth EBP plus 4 dereference. The dereferencing of EBP is done in this function, the continued dereferencing. So if we look at the implementation here, first, where do we start? If we're provided with a context pointer, then we pull it out of the context pointer and assign what's called here EBP of caller to that. Now that's really the EBP, not a caller in this case. This is the EBP of the context, but that's the naming here. So in the case of that not being true, here we're just taking the register value, okay, and making that to be pointer to void. I don't know why it doesn't come. Oh, because it's declared as a pointer to void. turning that into an address and then star that, taking the star of that, and that is again called EBP of caller. Now if U is 0, this doesn't get entered, otherwise it loops U times, right? If U is 1, it loops 1, just continuously dereferencing. Now the question is, which EBP is this going to return? If I call this function, am I going to get my own EBP back, or am I going to get the EBP of the function that called me? Well, that's easy enough to test by simply running that function. It's a static function. If I do this and don't provide any argument, then that's 0. And first I'm going to run up to here and see what my EBP is, and see if this returns my EBP or something else. Remember, EBP does not change throughout the entire duration of a given function. So I can call this anywhere within this function, and it should return the same value. Oh, I don't need that right here. Just look at the register. That says 97FF08. That's my EBP. That's my EBP, right? Now let's see what this gives. That's why it's acting up. It needs to be clean. So I modified, during the explanation, I modified this file, and it hasn't, somehow it hasn't gotten into the debug program database, I guess. So I'll just pause this and let it build. Okay, here we go. Hopefully it won't complain. Now our EBP is 97FF08. That's easy enough to remember. It'll be the same when this function returns. I can just step over. Well, let me step over it first. See what we get. Now that's the same value as this value, right? So how is it possible that that came out to be the same when this thing did a dereference? The reason it's the same and not the same, the reason it is the same, and the reason why this thing has to take at least 1 star is because this EBP, the EBP of this function, is not my EBP, right? So it has to at least do 1 star to get my EBP out. So here, it's doing the 1 dereference. This is invalid at the moment. Here's the value that this function has as its EBP, which has been just retrieved from the register. Star of that, right, is my EBP, because EBPs are like a linked list. U is 0, so we'll just return. And so therefore we can retrieve our own EBP. And if I want to get the caller's EBP, I just need to put a star in front of this address. I can call this my EBP, and address EBP caller. equals star. Now that should work, even though we have no way of verifying it. It'll give a different result, and that's how you walk a stack frame. It's like a linked list. The way to verify it, I guess, would be to use the debugger, but the debugger is doing the same thing we're doing. So if I take star of this address, that says 97FF1C, and I don't know if this thing, here's the function that called us. I went back to the Unicode build. FF1C, which is what we got. We got to come back here. FF1C. See? I thought I'd change this back to the. I didn't. Okay. So that's the reason for this star operator working the way it does. So this is not, I mean, well, the thing itself, this address thing, also has a way to extract the address. So if you wanted to interpret one of these addresses as something else and take a star, right? Suppose I want to consider this to be a pointer to ints or something. Then I can use the pvoid cast that this thing has, okay, so the operator pvoid, and then I could say that I've been thinking of this as a, I don't know, a car star. Pointer to constant character star, right? And then I could take star of that, and star of that would give me a car. Right, so you can still do everything you want with these addresses as in terms of just a regular old address, but you have to cast it. You have to pull out the pvoid member first, which you compile, in order to treat it as a different type of star. A regular star is just going to do that UBP walk, which you don't always want. Now it's compiling fine, but that's a perfectly fine statement. And where's the header file going? Oh no, here I'm in it. I'm in the header file. Okay, now here is a function called return address. There is a compiler, what they call an intrinsic function. This used to be called caller's address, but in the last video I realized that that's not a good naming. Return address is the better naming. That's the address to where the function I'm currently in will return on a return statement. Okay. Now I'm going to just show you, because there is such a thing, but you have to include a special file in trin.h. To make it constant. Return address, I'll use the compiler intrinsic. Okay. And another way, well, I'll use this thing, which returns an address value, right? going to show you that these two values are the same, and it doesn't matter where I am in the function. Where the function is going to return to is going to be the same throughout the function. And that is obtained by obtaining the EBP value and adding 4 and then taking the star of that. I mean, putting it in brackets or whatever you want, dereferencing it. Okay, using the compiler intrinsic, which I haven't really explained, but it says 4010E9. If I do this, you can see it's the same value, right? So this has the meaning of this. Now what does this do? If we look at the disassembly, for return address, the reason this is called an intrinsic function is because this function is not a function at all. It just emits the code for this into your code. And what it has done is moved into EAX the value at EBP plus 4, which is where the return address is stored. And now it's storing that into this local variable, which is at EBP minus 4, turns out. Okay? Whereas this one is calling, the one I'm using is calling a function. And what the function is doing is to get the caller's return address, it needs to do get EBP, right? If u is equal to 0, I have to get the EBP not of this function, but of the function calling this function. So this amounts to a plus 1 here, because that's null. There's a p context here, because this function takes optionally a p context, adding 4 and then taking the star of that, which gives me an address. You see, it ends up being the same thing, except we're in the wrong function to do a simple get EBP. You have to go one step further to the caller's EBP, add 4, take star, and that gives me my EBP. So these have the same effect, and that's that. So I can get my return address anyway this way. Another way I could get my return address is to get my EBP, add 4, and star. That's all that function is doing. And that's all this function is doing, as you saw. It took the real EBP immediately, added 4, and then put it down in square brackets, and then stored that on the stack. I'll show you that this also has the same effect. Here I don't need to add 1 because I'm already in the function that I'm concerned about. Then we get the same value. Okay, now that's the address where we're going to return to. That should be the address in wmain here. Okay, where we're going to return to, and that's this value, 4010E9. Just remember that, 4010E9. 4010E9, same thing. That's the address where we're going to return to. Now, if I want the address that the caller is going to return to, that is the next one in the stack frame, in the stack walk, I could put a 1 here. So get the caller's EBP, add 4, and take star of that. That will give the address where the caller will return to. And that's what this one will do for you. At least you can do the same thing. but it becomes kind of tricky with the stars and the casting and all that. Okay, now I'm just going to run this, see what the value is. 4194D2. Now that should be in here. That should be this address, 4194D2, which is the position that this W main will return to when it's finished its business. Okay? So remember that number, 4194D2. Back to main, W main, 4194D2. So that's the address that this function will return to. Alright? And that's all there is to walking the stack. Eventually this thing returns null or something invalid, completely invalid, unreadable, which you can test for. Another property that this thing has is, first what I could do is I could retrieve this address, right? And I could say, if I can I read it? Now, this square brackets means, can I read 4 bytes worth of data from this address? If that returns false, then I'm not going to attempt to try and read the value there, right? I'm not going to try to, I might print out this address, but I'm not going to try to go any further because, looking at what's there or something, because that would cause a crash. This thing allows you to avoid a crash by testing the readability of a particular address. True means you can read from there, false meaning you can't. And I guess the rest of it, now there's one more thing I have here. Current address gives you approximately what the current address is. It's not an exact value. It's the value where this call was issued. But it's not really the address of this line in C++ code. It could be anything. But it gives you an approximate location of where you are. Oh. And once this compiles, I'll run it here, and I'll show you that where the call is issued is in fact the value that will be returned. And that's not necessarily this line. Okay, now the call is here, so this function should return 401 for A1 where the call is made, right? That's where the call is issued, and it's going to return the address where the call was issued, which is not the address that we're currently at, which is a B here. So try to remember that number. Well, I can step through it. 401 for A1. There it is. See? 401 for A1. So that's approximately where this line is in the code. It won't be, the next line will be further along in the code than this one. So you can say with certainty that this address is less than the address of the next instruction. And you can also use this address to determine what function you're in, and so on. Okay, that's it for that. A quick update or overview of the TsAddress class, a very handy tool for walking stacks and for adding and subtracting numbers to addresses without regards to the size of the objects contained at that address. Simple, just like assembler integer differences. Okay.